Welcome to Theory of Computation. Today is lecture number 30. What we have been discussing is the theory of NP completeness. We started with this very famous theorem called the Cook-Levin theorem, which told us that SAT was NP complete. So that was the first problem that we showed was NP complete. That means it was in the class NP, and every problem in the class NP was polynomial time reducible to it. From now on, when I say a problem A is reducible to problem B, I would always mean that it is reducible in polynomial time. This is going to be the terminology that we are going to use for the rest of the lectures on NP completeness. Whenever I say a problem is reducible to another problem, we will implicitly assume that I am also saying that it's reducible in polynomial time. So SAT is a problem such that everything in NP is reducible to it. Then we looked at another problem, and that was a very, very restricted version of satisfiability. But that problem also came from propositional logic, and that problem was called 3-SAT. In this problem, you're given a formula, a Boolean formula over n variables. However, you're guaranteed that the Boolean formula is going to be A in conjunctive normal form, and B, every clause will contain exactly 3 literals. Remember, a literal is just a variable or its negation. So in 3-SAT, you are not only given a Boolean formula, but you're also told that the Boolean formula is going to be of a very special form, that is conjunctive normal form, and each clause is going to have exactly 3 literals. And what you have to do is tell whether this formula, this very special formula, is satisfiable or not. Well, you may ask the question, which is a technical question, what if somebody doesn't give you a formula which is not in conjunctive normal form? So if somebody hands you a formula which is not in conjunctive normal form, what are you expected to do? Well, in that case, you can reject the input. That's a bit like when we say you're given a formula, remember that you're given an encoding of the formula. Now, if somebody gives you an input which doesn't correspond to a proper encoding of the formula, you'll simply reject the input. So, since it's very easy to check if a formula is in the right form or not, so therefore we will not concentrate on that part of the problem. The real problem is when you get this formula in this restricted form, which is conjunctive normal form with each clause containing 3 literals, can you tell whether this formula is satisfiable or not? And then we pose this problem as a language, as we always do. So 3-SAT is the set of all encodings of formulas which are in conjunctive normal form and each clause contains exactly 3 literals and are satisfiable. So this is the problem that we are looking at. And of course, we are not finding algorithms for this problem. We actually proved that this problem was NP complete. So what we did was we showed how to reduce SAT to 3-SAT. And this reduction was a polynomial time reduction. Now, since we know that SAT is NP complete, that is, all the problems in NP reduced to SAT, therefore, all the problems in NP also reduced to 3-SAT. So, what is this theorem actually telling us? Well, it's telling us that what we can do is we can restrict our formulas, and if we put the restriction that the formulas have to be in 3CNF, then we do not make the problem any easier. It still remains NP complete. Well, you may ask if there is another restriction we can put on the formulas which will make this problem easier, and the answer is yes. So, for example, if I tell you that you have to now look at the problem 2-SAT, which you might have guessed by now what it means. 2-SAT is the problem in which you'll be given a Boolean formula, and this Boolean formula will be in conjunctive normal form, but now every clause will have exactly 2 literals. If we look at the problem 2-SAT, it turns out that one can find a polynomial time algorithm for 2-SAT. So thus, the problem 2 sat is in the class P? Well, most of the computer scientists believe that the class P is not equal to the class NP. Therefore, no problem which belongs to the class P can ever be NP complete. This is once again just in speculation. We do not have a proof of this. I keep repeating this, that we do not have a proof of the fact that P is not equal to NP, because it's very important for you to understand that NP completeness is overwhelming evidence that a problem doesn't have a polynomial time, but yet till today it is not a proof. So I was telling you about 2 sat. So if you restrict your Boolean formulas to be in conjunctive normal form, where every clause contains exactly 2 literals, then it turns out that the problem does become easier and one can find a polynomial time algorithm for it. So you see, when you put certain restrictions on your formulas, the problem becomes easier, and however there are certain restrictions which you put on your formulas, the problem doesn't really become easier, it still remains NP complete. And that's what the previous theorem told us. So let's see what we have learned so far about NP complete problems. In the last lecture, we showed that 3 sat is NP complete. This is our second problem that we have shown to be NP complete. Now we know, and we have seen a proof that sat is NP complete, which is essentially the Cook-Levin theorem. And the second fact we know now is that 3 sat is NP complete. We proved it in the last lecture by reducing sat to 3 sat. So that's our current knowledge of NP completeness. We know of 2 problems which are NP complete. One of them is sat and the other one is 3 sat. Of course, both these problems are very closely related. They are both problems about Boolean formulas, about propositional logic. Now, what you can ask is, if all problems that are NP complete, do they come in this flavor? Do they always have to do with Boolean formulas? Or there are other kinds of NP complete problems? That's a very interesting question. And as we will see, there are other kinds of NP complete problem which, when you look at them superficially, look very different from satisfiability. So today we would explore a problem in graph theory, which is a completely different subject from Boolean logic, propositional logic, and actually prove that one of the problems that comes from graph theory is NP complete. And we will follow our old recipe. We don't have to reinvent the wheel. We don't have to show that everything in NP is reducible to this graph theoretic problem. What we can do is, we can take a known NP complete problem and reduce it to this graph theory problem, and that would establish the fact that this problem is NP hard. And then it would be your homework to actually go and prove that the problem does belong to the class NP, and therefore it is NP complete. So that's what we will do. Today we will look at a graph theory problem and prove that it's NP complete. So let us now show that a problem from graph theory is NP complete. Note that so far we have only 2 known problems that are NP complete, and they're both from propositional logic. But in order for us to come up with this new problem in graph theory, we will have to review some definitions from graph theory. So you should now go and review your basic discrete math course and all that you know about graph theory and the notation of graphs. I would be going very quickly over it. I would assume that you know what a graph is. Remember, it's just a graph is given by a bunch of vertices, a finite set of vertices, and a set of pair of vertices that we call edges. So a graph G will be given by V, E, where V will be the set of vertices and E would be a set of edges. Now what I am going to do is present to you a definition of what an independent set is inside a graph. So this definition says that suppose you're given a graph which is given by V, E, so V is the set of vertices and E is the set of edges. And now what you do is you take a subset of the vertices. So what you do is, out of all the vertices that are in the graph, you choose a subset. And what I will tell you is when to call this subset an independent set. We will call a subset I of V an independent set if the vertices of I have no edges between them. So, formally speaking, for all x comma y in I, where x is not equal to y, the pair x comma y is not an edge in the graph. So, intuitively, what you're doing is you're looking at a subset of your graph, a subset of the vertices which have no edges between them. So if you focus in or zoom in on these edges, what you would see inside I will be the empty graph. So let's look at a few examples and try to digest this concept before we start defining our problem. So on the screen there's a graph shown to you, and this graph has 10 vertices. And in this graph, if you look at this set of vertices, which is A, C, D, and G, then you realize that there is no edge from A to C, there is no edge from A to D, there is no edge from A to G. Similarly, there is no edge from C to D or C to G, and DG is also not an edge in the graph. So in this set, there are no edges, and therefore this set is an independent set. So in this graph, we saw an independent set, and this particular independent set consisted of 4 vertices. Let's have a look at another graph. So now this figure shows a graph on 12 vertices, and in this graph also we have an independent set. It's B, C, F, J, and K. So if you look at these 5 vertices now, B, C, F, J, and K, they form an independent set because there is no edge between them. So here's another example of a graph and a subset in it, and since this subset has no edges in between them, therefore I'm going to call this subset an independent set. So an independent set is just a terminology for a subset of vertices where there are no edges between these vertices. Let's look at one other example of a set which is not an independent set in a graph. The figure shows a graph on 12 vertices on your screen, and if we look at the set A, B, C, D, that is not an independent set because A, B is an edge in the graph. So if I look at this set A, B, C, D, then since there's one edge which is between the vertices of these set, therefore I will not call this set an independent set. So you see, if you have a subset of vertices and there's even a single edge between them, we would say that that set is not an independent set. On the other hand, if you have a subset of vertices which have no edges between them, then we'll call that set an independent set. So the terminology of what an independent set is should be clear by now. Now what we're going to do is define our computational problem. So let's look at the computational problem that we are going to define. So let us define this language which we call independent set, and this consists of all pairs G, K such that G is a graph which has an independent set of size K. So what you do is you collect all graphs G and integers K such that the graph has an independent set of size K. What is being asked computationally? Whenever you are given a language, you must ask yourself the question, what is the computational problem that I am required to solve? Well, the computational problem is as follows. You'll be given a graph and an integer K, and you have to tell whether the graph has an independent set of size K. So suppose I give you a graph on 10,000 vertices and I give you the value of K, say 35, then you will have to find out if there is a set of size 35 which forms an independent set in this graph. So that's the computational question. And the language, of course, is the set of all pairs G, K encoded properly such that G contains an independent set of size K. Well, once again, we're doing the theory of NP completeness. So we're not going to give any algorithms for solving this problem. What we want to do is we want to prove that this problem is NP complete. So let's start with doing that. The first thing that we want to show is that independent set is in the class NP. So how do we show that a problem is in the class NP? Well, we have to give a polynomial time verification algorithm. Or if you prefer, you have to give a non-deterministic Turing machine that accepts that language and runs a non-deterministic polynomial time. Actually, showing that independent set is in the class NP is extremely easy. It's very easy to come up with a verification algorithm for the independent set problem, and therefore I've left this part of proving that independent set is NP complete as an exercise for you. The only hint that I'm going to give you is, suppose if I give you a graph and an independent set, it should be very easy for you to verify that the independent set is indeed an independent set. And I think actually this one line is, after a little while, after you work with NP completeness more, should be a proof that independent set is in the class NP. Once we have done that, now the second thing we have to do is show that independent set problem is NP hard. So we have to show that every problem in the class NP is reducible to the independent set problem. But remember, now we do not do that. We actually take a known NP complete problem and reduce it to our problem. That was the recipe for proving NP completeness that we came up with in the last lecture. And that's what we are going to do in this lecture also. In order to prove that the independent set is NP complete, we will just take one of the known problems, and right now our repertoire of the known problems which are NP complete is very small. It consists of only 2 problems. So we'll take one of them and reduce it to independent set, and thereby showing that the independent set is indeed an NP complete problem. So now we want to show that the independent set is NP complete. All we'll have to do is to show that 3-SAT is reducible to the independent set problem. Once again, here I want to emphasize that we will show that 3-SAT is reducible to independent set. 3-SAT is a concrete problem. It's just one single problem. And we'll reduce it to independent set, and that will show us the NP completeness of independent set problem. And this is much, much easier than what Cook and Levin had to do. They had to show that all problems in the class NP are reducible to SAT. What we're doing is building on their work and just showing that 3-SAT is reducible to independent set problem and obtaining the same result for independent set problem because we are implicitly using their theorem. So we will show that 3-SAT is polynomial time reducible to the independent set problem, and this is much, much easier than what Cook and Levin had to do. So let's go ahead and do this. Note that in this case, I actually had a choice. I could have chosen to reduce satisfiability to the independent set problem, or I could have chosen 3-SAT to reduce it to the independent set problem. Well, you may ask, which one do you choose to reduce? So which one of the known NP complete problems will you choose? Well, the answer is you will choose the one that you find easier to deal with, which seems closer to your problem. One answer is that you can choose any one of them, but that's a theoretical answer. That doesn't really tell you which one to choose. The other answer is you choose the one which seems easier and give it a try. So let's go ahead and prove that 3-SAT is polynomial time reducible to the independent set problem. So the theorem that we want to prove is that 3-SAT is polynomial time reducible to the independent set problem. Consequently, the independent set problem is also NP complete. So let's think about what we will have to do. We will have to come up with a reducibility from the 3-SAT problem to the independent set problem. So let's spell out this reducibility. You will have to once again recall the definition of what a reducibility is. Not only you have to recall the definition, but I would recommend you actually digest the definition of what a reducibility is. This means we have to give a function from sigma star to sigma star. So we have to give a function which takes inputs for 3 SAT and converts them into inputs for independent set problem in such a way that the formula is satisfiable if and only if the output graph has an independent set of a given size. So let's spell out what this reducibility will have to do. We will have to show that given a formula phi, we can construct a graph, let's call it g sub phi, and an integer k such that phi is satisfiable if and only if g sub phi has an independent set of size k. As we're dealing with 3 SAT, and as 3 SAT is NP complete, therefore we get to assume here that phi is in 3 CNF. So phi is a formula which is in conjunctive normal form, and every clause has 3 literals. So you see, because we are using 3 SAT, we get to assume something about our Boolean formula, which is the input. If I would have instead chosen to reduce 3 SAT to independent set problem, then I could have not made this assumption. In this case, 3 SAT is a restricted version of SAT, and I know that is also NP complete, so I get to assume something for free, which is that phi is in conjunctive normal form, which is the important part, and the second thing is that each clause has 3 literals. Now what I will do is, I will describe to you this reducibility. I will describe to you how, given a formula phi in 3 SAT, you will calculate this graph g sub phi by an example. So first let's look at an example, and then we'll describe this graph g sub phi in general, and then we'll prove that this is indeed a polynomial time reducibility. So let's take this formula which is written on your screen, and this formula has 3 clauses in it, and the clauses are, the first clause is x1 or x2 or x3 bar, so it has 3 literals. The first clause is ended with that is x1 bar or x4 or x5, and the third clause is x2 or x3 bar or x4 bar. So from this formula we'll make the following graph in the following way. So I'm describing to you the way in which you will make this graph from this given formula. First of all, for each clause we will place a cluster of vertices and connect them all to each other. Each cluster will have 3 vertices, and these vertices will be labeled by the literals in this clause. So what you would do is, you'll go through this whole Boolean formula, and for each clause you'll make a cluster of vertices. So if the formula had m clauses, you will get m clusters of vertices. Each cluster will have 3 vertices in it, and now you will label these vertices with the literals in that clause. And that's the first part of the construction. So once you read the whole formula, you will know what are the vertices in this clause. What about the edges of this graph? How will we construct the edges? Well, one of the instructions is that inside a cluster, all the vertices will be connected to each other. So that's some of the edges. Within a cluster, every vertex will be connected to every other vertex. Now what will happen between clusters? So between clusters, suppose if you have a vertex xi, it will be connected to all vertices that are labeled xi bar. So every variable vertex xi will be connected to its negation, all the vertices that correspond to its negation. So xi will be connected to all occurrences of xi bar in the graph, and xi bar will be connected to all occurrences of xi in the graph. So in this example, let's see how this graph is made. So the first cluster in this case consists of 3 vertices which are labeled x1, x2 and x3 bar. Those were the vertices which were in the first clause, and as you can see, all these vertices are connected to each other. The second cluster consists of 3 vertices x1 bar, x4 and x5, and within these clusters, all these three vertices are connected to each other. The third cluster contains these vertices which are labeled x2, x3 bar, and x4 bar, and once again they come from the third clause. You will see that there are edges between these between clusters that go across. So for example, the vertex which is labeled x1 is also connected to the vertex which is labeled x1 bar. The vertex which is labeled x2 is connected to all the vertices that are labeled x2 bar, and so on. So this is the way we have made this graph. So the construction of this graph is extremely simple. If you think about it, this graph is nothing but a way of coding up this formula. So if I show you the formula, you can easily come up with this graph. On the other hand, if I give you this labeled graph the way it is, and label it like this, you would be able to tell me what the Boolean formula was from where this graph came. So this graph is nothing but a way of writing down this formula. Now what we want to do is we want to think about an independent set in this graph. How will an independent set in this graph look like? Now suppose that phi has m clauses and n variables. Then we realize that G sub phi will have m clusters. Remember that we make one cluster for every clause. Now our first observation is the following. Any independent set must have at most one vertex from a cluster. So let's repeat this and see why that is the case. My claim is that if you look at any independent set, it can only have at most one vertex from a given cluster. Well, the reason for that is very simple. Remember that a cluster contains three vertices which are all connected. So if you pick up two vertices from a cluster, you'll end up picking up that edge also. And that would mean that that set would not be an independent set, because an independent set is one that has no edges inside it. So if you pick a set that has no edges inside it, then you can only pick one vertex, at most one vertex from each cluster. This means that the largest independent set in this graph cannot have size which is more than m. So what we do is, by this simple observation, establish the fact that the largest independent set in this graph has size less than or equal to m. Now what we will do is we'll ask ourselves, when does this graph have independent set of size exactly m? So now let's look at this question and think about it for a moment. So now our second observation is that if xi in one cluster belongs to the independent set, then no xi bar can belong to the independent set. Why is that? So suppose a vertex xi was picked up from some cluster. Then my claim is I cannot pick up xi bar from any other cluster. Well, that's by construction of this graph. Remember that the variable xi was connected to all the variables xi bars. Thus, if I pick up xi in an independent set, then I cannot pick up xi bar because they are connected. Or in other words, if you pick up xi from one cluster and xi bar from another cluster, then what you have done is actually picked up an edge of the graph, because xi and xi bar are connected. Thus, an independent set will have only vertices labeled xi in it, or only vertices labeled xi bar in it. So that's another property that we know of the independent set. An independent set can hit each cluster at most once, and the second thing is, if it picks up xi, then it cannot pick up xi bar from any other cluster. Similarly, we make the observation that if xi bar in one cluster belongs to an independent set, then no xi can belong to that particular independent set. And that is just taking our logic and reapplying it to the literal xi bar. So what does this mean? Thus we can think of the vertices in the independent set as an assignment of the variables, or we can think of the set of vertices in the independent set as being set true by an assignment in that cluster. So every independent set in this graph corresponds to an assignment of the variables. All the vertices that are in the independent set are assigned true, and all the vertices that are not in the independent set are assigned false. Let's make that assignment and see what happens. Now let's see. Suppose that I tell you that I can find an independent set of size m in this graph. This means there's a way that I can assign variables which are in the independent set, I assign them true, and that would satisfy my formula, because I am assigning one variable in every clause to be true. Why is it that this corresponds to a proper assignment? Well, the only way to violate a proper assignment is if I were to set xi equals true and xi bar equals true. But that's not allowed because those vertices are connected by an edge. So if the independent set picks up xi, it is not going to pick up xi bar. So I can set xi equals true, and automatically that would set xi bar equals false. And since this independent set hits all the clusters, therefore assignment will make at least one variable true in all the clauses. So our formula will be true. This means that if there is an independent set that contains m vertices, it must contain one vertex from each cluster. Thus the corresponding assignment must make the formula phi true. So we have constructed this graph G sub phi in a very special way. What happens is the satisfying assignments of phi correspond to independent sets of size m in this graph, and the independent sets of size m in this graph correspond to the satisfying assignments of phi. Thus there is a one-to-one correspondence between satisfying assignments of phi and independent sets of size m in this particular graph. So let's look at what is the theorem that we have actually proved. What we have proved is that if phi is satisfiable if and only if G sub phi contains an independent set of size m, where m is the number of clauses in phi. Once we have done that, it is very easy to see that G sub phi can be computed in polynomial time. So this shows that 3-sat is polynomial time reducible to independent set problem. Thus the independent set problem is NP complete. If you look at this proof, or if you think about it a bit, what did I do? I took a formula phi and I showed you how to construct a graph G sub phi from it, such that phi is satisfiable if and only if G sub phi has an independent set of size m. However, I did not give you a polynomial time algorithm which will take this formula phi and convert it into a graph G sub phi. But that's only details. If you think about it a little bit, given this formula phi, you can write an algorithm, you can write a very simple program that can compute the description of this graph G sub phi. Let's go a bit in detail and think about what such an algorithm will have to do and whether this can be done in polynomial time. What this algorithm has to do is take the formula phi and read it and count the number of clauses in it. Then this algorithm will also look at how many variables are in this formula. So there will be two counting programs which would actually count the number of variables and the number of clauses in this formula. Then it can start outputting the clusters, and once it's outputted the clusters, then it has to figure out what is going to be the edge set of this graph. And what it will do is, in each cluster that it is outputted, it will go and look at a variable and then go through all the other clusters and connect it with all the variables which are the negation of this particular literal. So it does not seem to be very difficult to design a polynomial time algorithm which will take this formula phi and output the graph G sub phi. Actually, you can even do better than designing a polynomial time algorithm. What I want you to do is think about this a little bit and actually try to prove that you can even compute G sub phi from phi. So you can come up with an algorithm which takes as input phi in 3CNF and outputs G sub phi and runs in logarithmic space, which is even more restricted than polynomial time. So this reducibility can be easily implemented. Now, if you really want to be very formal and pedantic about proving the NP completeness of independent set problem, then you would give the reducibility by the following algorithm. So formally, this reducibility is given by the following algorithm, which on input phi counts m to be the number of clauses in phi, and then it computes G sub phi, and it doesn't just output G sub phi, but it also outputs m along with it. So the formula phi is being mapped to the pair G sub phi comma m. So given a formula phi and being able to tell whether it is satisfiable or not is the same question as given this graph G sub phi and being asked whether it has an independent set of size m or not. So what we have shown is that 3SAT is polynomial time reducible to independent set. Consequently, this proves that the independent set problem is also NP complete. So let's think about what we have done in the theory of NP completeness so far. We started with satisfiability, which was proven to be NP complete via the Cook-Levin theorem, and then we showed that 3SAT is NP complete by reducing SAT to 3SAT. And now what we have done is reduced 3SAT to the independent set problem and thereby showing that the independent set problem is also NP complete. So we have the reducibility SAT is polynomial time reducible to 3SAT, which is polynomial time reducible to independent set problem. Now let me ask you a question. Is it true that the independent set problem is polynomial time reducible to satisfiability? Now I'm asking you the opposite question of what we have actually proved. We know that SAT is reducible to 3SAT, which is reducible to the independent set problem. Therefore, by transitivity of polynomial time reducibility, SAT is also reducible to the independent set problem. So now the question is the independent set problem reducible to satisfiability? And of course, here once again I'm talking about polynomial time reducibility. Well, the answer to this question is yes, that independent set problem is reducible to satisfiability. And what is the proof of that? Well, the proof is the Cook-Levin theorem. The Cook-Levin theorem says that everything in NP is reducible to satisfiability, and independent set is one instance, one problem in the class NP. In fact, what we can easily say is that all NP complete problems are polynomial time reducible to each other. That follows from the very definition of NP completeness. Remember that a problem is NP complete, it has to satisfy two requirements. Every NP complete problem satisfies two requirements. A, that it is in the class NP, and B, that everything in the class NP is reducible to it. Therefore, if you take any two NP complete problems, they must be polynomial time reducible to each other. Thus, the set of all NP complete problems is problems which are polynomial time equivalent to each other. What equivalence here means is that I can reduce the one problem to another and the other problem to the original problem. So if we view the class NP-complete or the subclass NP-complete from polynomial time, from the point of view of polynomial time computation, then they're all equivalent to each other. Well, what I want to do now is to talk about two other problems in graph theory and show you that they are also NP-complete. These problems are going to be very closely related to the independent set problem, and therefore the reductions are not going to be very difficult at all. And this is going to be our theme. Proving that problems are NP-complete is not very difficult at times, provided you choose to work with the right problems. And we'll see this point coming across in these examples. These examples are also from graph theory, so we'd look at two problems from graph theory and prove their NP-completeness. What we will have to do is review a few concepts from graph theory in order to define these problems properly. Let's have a look at these problems. What I want to show is now two easy reducibilities. The first one is almost trivial. Although this reducibility is quite trivial, but I will go through it very slowly in order for you to understand it properly. Let us define a new problem in graph theory. Well, let's start with the graph G equals V comma E. Once again, V is the set of vertices of the graph and E is the set of edges. Now let's take a subset C of the vertices and we'll call it a clique if all the vertices in C have edges between them. So what I want to do is, I'm given a graph and I'm looking at a subset of vertices of this graph. So I look at a few vertices of this graph, and if all these vertices are connected to each other, if they're all possible edges between the vertices, then I will call this set as a clique in my graph. So formally, what C is a clique if for all x comma y in C, where x is not equal to y, xy should be an edge in the graph. So if I take a set of vertices and every pair between them, a subset of the original vertices, and if every pair within this set has an edge in it, then I call this subset a clique in the graph. For this concept to get clear, let's look at a few examples of graphs and cliques inside them. So the figure on the screen shows a graph on 10 vertices for you, and in this case, if you look at this subset which is given by A, B, F and G, that forms a clique. So if you look at the vertices A, B, F and G, that forms a clique because A is connected to B, A is connected to F, A is connected to G, B is connected to F and F is connected to G. So you have all possible edges between these vertices. Therefore, we call this a clique in the graph. So a clique in the graph is nothing but a bunch of vertices which are all connected to each other. Let's look at another figure. So this figure shows you a graph on 12 vertices, and in this case what we have is the vertices A, D and F which form a clique in this graph. So this is a larger graph and it doesn't have very large cliques in it, and A, D and F are three vertices which form a triangle, so a triangle would be a clique. So remember, if I say I have a clique on one vertex, every vertex is a clique on one vertex. On the other hand, if I say I have a clique on two vertices, then I'm saying that I have two vertices that are connected to each other. If I say that I have a clique on three vertices, that means I have three vertices which form a triangle. If I say I have a clique on 12 vertices, well, that means I have a graph in which there are 12 vertices which are all connected to each other. So that's what a clique is. It's just a bunch of vertices which are all connected to each other. Let's look at another example. So now if you look at the next figure, this also has a graph. It shows a graph on 12 vertices. and in this case the vertices B, C, D, J and K form a clique in this graph. So this is another example of a graph, and this has a clique on 5 vertices. So inside a graph you can have cliques of various sizes, and we call a subset a clique if all the possible edges within that subset are present in the graph. So now once we have defined the notion of a clique in a graph, we can go ahead and define our computational problem. So let us define the following language, which we will call clique, and it's going to consist of all encodings of G, K, where G is a graph which has a clique of size K. So as a language, what you do is you collect all pairs G, K, where G is a graph and K is an integer, and the graph G contains an independent set of size K. Once again, once you get a language, you must ask yourself what is the computational question behind the language. So in this language, what you will be given, or in this computational problem, what you would be given is a graph and an integer. And what you have to do is find out whether this graph has a clique of size K in it or not. So that's the computational problem. Now, what we want to do is we would like to prove that this graph, that this problem is NP-complete, that this graph theory problem that we have posed is NP-complete. So we are not going to discuss any algorithms for finding cliques, but what we will do is show that this problem is NP-complete. So we are going to look for reducibilities. We are going to try to take an NP-complete problem and reduce it to clique. Well, in order to prove NP-completeness, remember we have to do two things. First of all, we have to show that clique is a problem which belongs to the class NP. How do we show that some problem belongs to the class NP? In order for us to do that, we have to simply give a verification algorithm. And this part is usually very easy. Showing that something is in NP is usually very easy, and therefore for this particular language I've left that as an exercise for you. So your exercise today is to understand this clique problem and understand the independent set problem and try to come up with a relationship between them. Try to find a reducibility from the independent set problem to the clique problem. That would be your homework for today. So in today's lecture, what have we done? Well, we looked at the problem 3SAT, and then we looked at a graph theory problem. If you think a little bit about this, what we have done is we have related two completely, which seem to be two completely unrelated problems. One is a problem which talks about the satisfiability of a given Boolean formula. The other is a problem in graph theory. And what we did was we showed that 3SAT was reducible to the independent set problem. What that did was it put the independent set problem in the class NP-complete. It proved that the independent set problem was NP-complete. We already knew from the Cook-Levin theorem that the independent set problem is reducible to 3SAT, and the independent set problem is reducible to SAT. So these three problems are polynomial time equivalent to each other. Our next task is to look at this problem clique and show that clique is NP-complete. Once we show that clique is NP-complete, we would realize that we have actually 4 problems which are NP-complete, and each one of them can be transformed into the other via a polynomial time reducibility. This means that these 4 problems in some sense are similar to each other, are same. If you solve any one of them in polynomial time, you would solve all of them in polynomial time. And the fact that these are NP-complete seems to say that solving these problems is equally hard from the point of view of polynomial time computations. Well, what we will do is continue this theme of NP completeness in the next lecture. I'll see you next time. Thank you and goodbye.